All right. Hi. I'm here to tell you about the latest in a series of attempts I've made to deconstruct logic programming into functional programming using types. Specifically, I'd like to combine data log, which is logic programming where all your relations are finite. So that's why it's called data log. It takes information from databases. We can execute queries using database joins. So it's nice and efficient, but also quite declarative. I'd like to combine it with higher order functional programming because otherwise it's a very first order language. It's kind of awkward to do modular or abstract programming in. And I'd like to add aggregation to it, which is a thing that everybody needs, but isn't in Datalog for some reason, because it's, and along the way, it will turn out that the things we need to get those three things also give us tensor algebra. So it gives us a generalization from relational algebra, which is sort of over Booleans, to things like matrices and matrix multiplication over the reals or many other types. And the tools I'm going to use to do this are some simple mathematical ideas. Maybe this should be, there we go. That's probably, be nice if I could get that. Oh, well. The tools I'm going to use to do this are finitely supported maps, pointed sets, and point preserving maps. And I'm going to define all of those things. So first question, why isn't logic programming just functional programming? Here's a simple logic programming. It defines follows in a social network, and then two people are mutuals if they both follow one another. So a logic programming defines a bunch of relations. Relations are sets, which are functions into Booleans. They tell you whether something is in the set or not in the set. So following this intuition, I can write a little functional program that does exactly the same thing, or seems to, right? I can say when two people follow one another, it turns into a big OR of ands of equality tests. And I can define when two people are mutuals, if both of them follow one another. So semantically, these seem the same, but operationally, they are not the same. There are things I can do in the logic program that I can't do in the functional program. For example, I can ask, who are the mutuals of eta? In a functional program, functions are input-output black boxes. You cannot ask, what are the things that make this function true? You can only ask, is this function true on these arguments, right? So semantically, seems fine. Operationally, doesn't work out. And we can see that it continues not to work out if we make our logic program a little more interesting. Let's say, who are the co-stars? If we have a database that says this film stars this actor, two actors are co-stars if they starred in the same film. Okay, let's try and turn this into a functional program. I'm going to assume I have a function stars. Now I'm going to try to define co-stars. Where does the film come from? So, how do I get film into scope? Well, let's think about the semantics of the logic program. It's true, the head is true, if there exists a film that makes the body true. So let's suppose we have a magical function exists that takes a function from films to Booleans and tells me whether something satisfies it. Then I can write my program. I can say X and Y are co-stars if there exists a film that they both starred in. The problem, of course, is that exist is basically unimplementable. You could, I guess, enumerate all possible films and test them all. But A, how did you figure out how to enumerate all possible films? And B, this is really, really inefficient. This is not how the program on the left executes. It uses a relational join. It uses stars to find the films that they might have co-starred in. So what I really want here is a function that is not an input-output black box, but which can enumerate its support, the things that make it true. Right? So that's the difference to me between functional programming and logic programming. Certainly with, right, in logic programming, our relations can enumerate their support. They can tell us things about the inputs to make them true. So this is what we need. And specifically, because I'm interested in data log, we're going to, in this talk about finitely supported functions, functions where there's finitely many things that make them true, and we're going to represent them as tables, literally input-output tables. Okay. A little bit of theory we're going to need to get to. What is the support of a function? Well, I'm going to slightly generalize from Boolean functions. I'm going to say we have sets, A, B stand for sets. We get pointed sets, which are just sets with a designated element, which we think of as the default element, right? I call it nil. Nil for Booleans is false, right, by fiat. And so the support of a function into a pointed set is all the inputs that give us a non-default output. So for Booleans, this is all the things that give us not false, so true. But for other types, it might be something else, right? And the idea is this means that if I'm representing as a table, I don't need to list the things that map to the default value. That's the default value. And so if they're finitely supported, that table gets to be finite. And then a finitely supported function is one whose support is finite. I'm going to write it with this little arrow with the fs over it. And turns out finitely supported maps themselves form a pointed type. The boring value is the empty map, the one that's everywhere the default value. Okay. So the goal now is I'm going to give a language that looks functional. It supports procedural functions, including higher order ones, but also supports finite functions. It has a type for finite functions. These are going to be guaranteed finitely supported by the type system. They're going to be represented by tables, and they're going to be computed like database queries. And in this talk, I'm mostly going to talk about point one. I'm not going to, represented as tables is relevant, but I'm not going to talk about how we compute them. I have ideas for that. Okay, here are some examples of programs written in this language. Here's our costars query. And in this case, you just write the thing, but you annotate that costars is going to be a finitely supported function. And it knows that stars is finitely supported, so it knows that the body of that exists is a finitely supported function, which is why you're able to run exists on it. Because since it is a table, I can enumerate the inputs for which it produces true. But we can also do things involving aggregations, like a summation, right? Find the count of films an actor has acted in as the sum over all films that the actor has starred in, producing 1 if they have starred in it. And if we work with, say, the naturals with infinity, where infinity is nil, we can do things like shortest paths, although this involves recursion, and I don't actually know how to do recursion yet. But like these are the kinds of programs I'd like to be able to write. So one question is, how do I ensure that these things are actually finitely supported? How do I check that? Well, in data log, this is really easy. You check that the head of your rule, all of the variables in it, are grounded by the body of the rule, right? And so here they obviously are. Let's translate this program into my syntax and notice that it gets a little bit more complicated. And in particular, in functional programming, our programs are not quite as flat as they are in logic programming. They are built up out of compositions of operations. So here's the translation of that program. How can we check that it's finitely supported? Well, we're going to have to figure out how to compositionally check which variables are grounded by an expression. And I'm not going to give the full details for that, read the paper, but I'm going to talk about and, or, and exists, because those are pretty much critical for logic programming. Okay, so let's talk about and or. Given some relation, edge, right? Which variables are ground in these two expressions? Edge xy and edge yz? Well, all three of those variables are ground by that expression, x, y, and z, right? There's only going to be finitely many x's that make that true. Same for y and z. But if I change that to edge xy or edge yz, only y is ground by that expression. Does anybody see why? Why doesn't this expression ground x, for instance? So yeah.
If x can be false, but if y instead of true, then it's still true, right?
Yeah, exactly, right? So suppose that edge yz is true, then it doesn't matter what value x has. So it's true for all of the x's if there's any edge in the relation. So t and u grounds x if either t or u does. T or u grounds x if both t and u do. But why? What is it about and or that's different here, right? Because if you think, I'm trying to do this with types, you might think and or have the same type, Booleans cross Booleans to Booleans. I claim no. We're going to invent types for them that make them different and that capture this difference. And the difference that makes and or behave differently is their behavior on nil. And produces nil if either of its arguments is nil. All right? It produces false if either argument is false. And this is important because it means that if either of its arguments constrains x to be a finite set, then t and u constrains it to be a finite set. because guaranteed to be nil, right? Right, the set of things that T and U is non-nil on is going to end up being the intersection of the set of things T is non-nil on and the things U is non-nil on. So if either of those is finite over a particular variable, this will be finite. Or only has the weaker property that it's nil if both of its arguments are nil. And so its support ends up being the union. It only grounds something if both of its arguments do. So this is what we need to capture, the difference between functions that preserve nil in each argument versus those that preserve nil only when both arguments are nil. So a little more theory. We're going to have to talk about nil preserving maps, right? The behavior of functions over pointed sets, do they preserve nil? Right? So I'm going to write point preserving functions like this with a lollipop, and they're just the functions that preserve nil. And they have the wonderful property that if I compose a finitely supported map with a nil preserving map, the result is still finitely supported. Because all the things that map to nil still map to nil. So if you only had a finite set not mapping to nil, it's still finite. It's only shrunk. So this already clues us into why nil preserving maps are useful. But what about nil preserving maps of more than one argument, right? That's what we're dealing with. We're dealing with and or, binary arguments. Well, it turns out there's two ways, at least two ways, to have a nil preserving map of two arguments. The simplest, most natural way is look on the left, right? We're going to define the direct product. I write with an ampersand. The direct product of P and Q is going to have as elements precisely pairs of a P and a Q. And nil is going to be the pair of two nils, right? This is the obvious way to define a product of pointed sets, right? Nil is nil comma nil. Or is a point preserving map out of this direct product because it preserves nil comma nil, right? Or of false comma false is false. And is more interesting, and it's going to take a different type. We're going to define the smash product of two pointed sets as saying, take their product, take the pairs, and then quotient. Say that a pair, x comma y, is nil if either x or y is. So all of those pairs, if either component is nil, the whole thing is smashed down to nil. That's why it's called the smash product. This captures exactly the property and has, right? And is nil preserving out of tensor smash, same thing. Because if either argument is nil, then by the rules of tensor product, the whole argument is nil, and therefore it has to send the result to nil to be point preserving. So these are precisely the two kinds of functions that are interesting to us on two arguments. The ones that preserve the direct product and the ones that preserve nil out of the smash product. And so these capture the different grounding behaviors, right? If you see a function out of the tensor product, it grounds like and does. It grounds a variable if it's ground by either of its arguments. If it's out of the direct product, it only grounds variables like or does. It only grounds those that are ground by both of its arguments. Okay, and then exists, we can now talk about the type of exist. It's actually pretty simple. Exist takes a finitely supported map into Booleans, and it produces a Boolean. Right? And it requires that its argument, the map, be finitely supported so that it can enumerate all of the things and check whether any of them is true. If it was an arbitrary function, we'd be stuck with the same problem we saw in the intro. How do I check whether something satisfies this? I don't know. But because I have a table of them, it becomes easy. And exists because it's a point preserving map. So why is exist a point preserving map? Well, what's nil at this finitely supported map type? It's the empty map. Is there anything true in the empty map? No, it's all false, right? And so that means that it grounds whatever its argument does, which is important. So the overall lesson here is if we want to check grounding in a functional language, we have to pay attention to what preserves points, what preserves nil. But the lovely thing is, as soon as we generalize from Booleans to pointed sets and point preserving maps, we enable ourselves to move beyond relational algebra. because there's lots of functions and lots of types other than Boolean that are pointed, and lots of functions on those types that preserve point. So for instance, at the top here, we have the composition of two relations. Composition of two binary relations is, does there exist an intermediate thing y, such that R holds of xy and S holds of yz? Below that is the definition of matrix multiplication. It looks exactly the same, except we change exists for summation and conjunction for multiplication. And what I claim is when you look at the types, when you look at these things as pointed sets, right? So Booleans is a pointed set, but so is the real numbers with the point being 0. When you look at the types of these operations, they match up and is a map out of bool smash bool. It preserves false in both arguments. Multiplication is a point preserving map out of the reals with 0 smash the reals with 0. It preserves 0 in both arguments. Right? 0 times anything is 0. Similarly, exists takes a finitely supported map into Booleans and tells you whether any of those Booleans is true. Sum takes a finitely supported map into reals, and it adds up all those reals. And so these type check in exactly the same way, which tells me that if I take two matrices, even if they're over infinite dimensional matrices, right? As long as they have the property that there's finitely many non-zero entries, then the composition, the multiplication of those two matrices, will also be finitely supported. It'll have finitely many non-zero entries. And in fact, the code to do relational composition and the code to do matrix multiplication, if you implement those, you can implement them the same way. All right. So we've now gone from relational algebra to tensor algebra. And there's loads of things that satisfy this pattern, right? So for example, if you want to do shortest paths, right? Take the naturals plus infinity, make infinity the point, the default value, and then plus acts like conjunction, min acts like disjunction, and minimum over a set acts like exists or summation, right? So we've now got aggregation as well. We've got tensor algebra and aggregation. So there's one thing that I haven't discussed is, I've said to check groundedness, you need to know when functions are point preserving. How do we check that a function preserves points? Again, for the full details, see the paper. But here is some intuition. Let's look at three functions: the identity function, a constant function, and lambda, the intersection of two sets, foo(x) and bar(x). Which of these preserve nil? Right. So foo here is not a finitely supported map. It's not a relation. It's a point preserving map. So is the identity function point preserving? Anyone? Yeah, because nil, lambda, if I apply it to nil, I get nil out. Is lambda x.true point preserving? No, I apply it to nil, I get true out. True is not nil. If I say lambda x.foo(x) and bar(x), and I apply that to something, and foo and bar are nil preserving, yeah, that still preserves nil, because foo(x) is going to be nil, and bar(x) is going to be nil, and nil is nil. So what we see here suggests that we have a type system where you have to use variables. Constant functions in general don't preserve nil. But it's okay to use them more than once. That's fine. And so we end up with a cousin of linearity. You've probably heard about linear type systems. You must use everything exactly once. You might have heard about affine type systems. You must use everything at most once. This is their cousin, relevant type systems, where you must use each variable at least once. No dropping variables. Again, the details are in the paper. It is slightly more interesting than that when you get to direct products. So remember, and takes a tensor product. There's also direct products. The rules are a little bit different. But that's the basic idea. So we end up with a type system that has three different kinds of functions. Ordinary functions, haven't really talked about those. Finitely supported maps, those are the thing that we invented this language in order to handle. And point preserving maps, which are important because they let us manipulate finitely supported maps while preserving finite support. Finite support we check via grounding, and point preservation we check via relevance types. So the overall idea here, relational programming or logic programming is about functions which know what their support is and can tell you what their support is, right? In data log specifically, it's about finite support. And most of this talk has been about that, but I claim that this applies to Prolog too. It's just that Prolog has a more interesting representation of support. It represents support in a sort of enumerable symbolic way. It enumerates a bunch of symbolic representations of the things that would make the predicate true. If you want to check support, you're going to need to know about pointed sets because those are needed to define support. And you're going to want to talk about point preserving maps because those are the ones that preserve finite support. And once you do this, you've naturally got a system that handles tensor algebra and aggregation, which is nice because everybody wants aggregation, and tensor algebra is pretty useful too. If you want to understand the type system in more depth, see the paper. It's a complicated type system. I kind of like it, but I have some ideas about maybe how to simplify it. It definitely has its warts. And I think I just have enough time for a demo. This is not entirely vaporware. I do have a prototype implementation. All right, is this readable to everyone? I hope that's big enough. Okay. So here is, all right, here's a little REPL. Here's a little program. This is defining a thing that says that such and such a person starred in such and such a film. So if I ask it, what is stars? Well, it says the stars of Casablanca were Bergman and Bogart. Here, #T means true, by the way. The stars of The Big Sleep were Bacall and Bogart. Okay, so let's go do our example. Let's go do costars, right? So I'm going to need to give it a type. It's a finitely sum-ordered map from, in this case, symbol is the representation I'm using for people, right? It's going to be a little function of 2 arguments. And we're going to say, okay, does there exist? Oh God, did I write exist with an F? Hold on. Exists as an S. Okay. Exists some film, which I'm going to give a type annotation. Film is a symbol, where stars film X and stars, I hate this thing, film Y. Oh, now I have to count parens. I hope I counted correct. Yes. Okay. Who are the pairs of people who co-starred? Well, Bacall co-starred with Bacall, apparently, because, of course, they acted in the same film together. But more seriously, Bacall co-starred with Bogart, Bergman with Bogart, and Bogart with both Bacall and Bergman. Let's go fix that. Let's add a little requirement that X and Y are not equal. There we go. That simplifies it. Okay. So that's a simple demonstration. There are also other interesting ones. So we had the film count example. So I have forgotten how to make things bigger in Emacs. There we go. Right. So I'm not going to type this out. I'm just going to load it. Right. So film count is, the function that takes an actor and gives me the sum over every film that they starred in of 1. Right. I load this, and it says in this tiny little database, Bacall acted in 1, Bergman in 1, Bogart in 2. All right. And you can pretty much read off the implementation of this from the typing derivation for it. Although the implementation is currently very stupid and doesn't do any real relational joins, but I have ideas about that. All right. And that, I think, is that. Thank you very much.